Most machine learning or AI failures do not happen because the model is bad in some generic way. They happen because the model is wrong in a very specific way. Sometimes the model is too simple. That is underfitting. Sometimes the model is too sensitive. It learns the training data almost perfectly but then struggles with new data. That is overfitting. And sometimes the model looks good in testing, passes the dashboard, and ships to production and then starts failing because the real world changed. This is where bias and variance stop being academic terms and become operational risk. By the end of this video, you'll understand three things: what bias and variance actually mean, why they create underfitting and overfitting, and why even a model that looks accurate can break when the data, the users, or the business environment shifts. We are going to build this intuition using this simple visual example: a model trying to learn a pattern from noisy data. And as we add complexity, you'll see the model moving from being too rigid to being useful to being dangerously flexible. Welcome to Scovia, where we make AI concepts feel like everyday ideas. Let's make this visual. Imagine these dots are real observations from a business system. Maybe we are trying to predict customer churn based on account activity. Maybe we are forecasting demand based on price. Maybe we are estimating risk based on transaction behavior. The specific example does not matter. What matters is that the data has two things happening at the same time. There is a real pattern and there is noise. You can see the pattern if you step back. The points are not random. They roughly follow a curve, but they do not sit perfectly on that curve. Some points are higher than expected, some are lower. Some may reflect unusual customers, imperfect measurements, one-off events, or plain randomness. That is what real data usually looks like: signal mixed with noise. Now, the model has a difficult job. It has to learn enough of the pattern to be useful, but it must not become so eager to explain the data that it starts treating noise as if it were signal. That tension is the entire story of bias and variance. Now let's fit a very simple model: a straight line. The model is trying to explain a curved relationship using a rigid shape. It captures the broad direction, but it misses the actual structure. This is high bias. Bias means the model has made assumptions that are too strong. It has already decided, in effect, that the world must look simple. The problem is not that it made a small mistake on a few points. The problem is that it is systematically wrong. It is wrong in the middle, it is wrong at the edges, it is wrong because the model class itself cannot represent the real pattern. This is underfitting. The model performs poorly on training data, and it performs poorly on test data. And collecting more of the same data may not solve the problem because the model is not flexible enough to use the pattern that is already there. In enterprise settings, bias often shows up as a model that feels blunt. A risk model treats different segments too similarly. A forecasting model may miss seasonality. A search ranking model may ignore context. A classification model may keep making the same mistakes in the same category. The model is stable, but it's stable in the wrong direction. That is high bias. Now let's make the model a little more flexible. Instead of forcing a straight line, we allow a smooth curve. The model captures the main pattern. It does not hit every point exactly, and that is a good thing. Some of those points are noise. A good model should not apologize for ignoring noise. This is the useful middle. The model is flexible enough to capture the real structure, but disciplined enough not to chase every accident in the training set. This is where generalization usually improves. Training error goes down, test error goes down. The model has learned something real. Not everything, not perfectly, but enough to perform well on new examples drawn from the same kind of data. This is the part many people miss. The goal is not the best possible fit to the training data. The goal is the best possible performance on data the model has not seen yet. The difference is the heart of machine learning. Now let's keep increasing the model's flexibility. At first, performance improves, but then something changes. The curve starts bending sharply to reach individual data points. It follows the small bumps. It reacts to outliers. It treats random noise as if it were meaningful structure. The training fit looks impressive. Almost every point is explained, but the model is no longer learning the underlying pattern. It is learning the specific accidents of this particular dataset. This is high variance. Variance means the model changes too much when the training data changes. If we collected a slightly different sample, the model might learn a very different curve. That is the signature of overfitting. The model performs extremely well on training data, but poorly on test data. It has not learned the general rule. It has memorized the examples. In enterprise AI, high variance can be especially dangerous because it often looks good during development. The training metrics look strong. The validation metrics may even look acceptable if the split is not realistic. The demo works, but when the model meets new users, new products, new regions, new behavior, or new edge cases, the performance drops. The model was not robust. It was too tuned to the environment where it was trained. This gives us the classic bias variance trade off. As model complexity increases, bias usually decreases. The model can represent richer patterns, it is less constrained, it makes fewer overly simple assumptions. But variance usually increases. The model becomes more sensitive to the specific training example. It has more freedom to chase noise. So we get this familiar shape. Training error keeps going down as the model becomes more complex. That part is not surprising. A more flexible model can usually fit the training data better. But test error behaves differently. At first, the test error improves because the model is learning real structure. Then it reaches a useful region. After that, test error starts getting worse because the model is no longer learning only the signal. It is learning noise. That is why training performance alone is not enough. A model that performs beautifully on training data may be the model you should trust the least. The real question is not how well did the model fit what it already saw. The real question is how well does the model behave when reality gives us something new. So far, we have assumed that the training data and the future data come from the same world. But in production, that assumption often breaks. Customers change, markets change, fraud patterns adapt, or product catalogs or policies or languages may evolve. The data distribution may move. This is why a model can look reasonable during testing and still break later. Bias and variance are not just development problems, they are production problems. A high bias model may fail because it never captured the real structure in the first place. A high variance model may fail because it was too dependent on fragile patterns in historical data. And even a well balanced model may degrade if the environment changes enough. This is especially important for enterprise AI systems. In a notebook, the dataset is fixed. In production, the world keeps moving. A model trained on last year's customer behavior may not understand this year's pricing changes. A document retrieval model that is trained on old knowledge articles may fail after a product launches. And a fraud model may degrade as attackers adapt. The issue is not just whether the model was good, it's whether the model is still good under the current conditions. So once a model fails, the first question is not simply which model scored higher. The better question is what kind of failure are we seeing? If the model performs poorly on both training data and test data, it is probably too simple. That is underfitting. High bias. If it performs well on training data but poorly on test data, it is probably too sensitive to the training set. That is overfitting, high variance. And if the training and test performance both looked good but the production performance declines later, the issue may be drift. The model learned a relationship that no longer matches the world it is operating in. This is where mature teams separate themselves. They do not just chase the highest score. Instead, they ask, is the model too simple? Is it too sensitive? Is the evaluation realistic? Has the data changed? Are we measuring what actually matters? That is how bias and variance become practical tools, not just textbook vocabulary. The answer is not simply to use a bigger model or a smaller model. The answer is to control the learning process. Start with a baseline, validate against data that resembles the real environment, control the complexity so that the model learns the signal without chasing the noise, and look at the actual errors, not just at the average score. And once the model is deployed, monitor it. Monitor the inputs, monitor the outputs, and the business outcomes. If there is a gap between the expected and the actual performance, then that's your clue that something is not working. Because a model is not finished when it ships, it has entered a changing system. So here's the intuition to remember: a high bias model is too rigid, it misses the real pattern, it underfits, and a high variance model is too reactive, it learns the noise, it overfits. A useful model sits between these two extremes. It is flexible enough to capture structure, but stable enough to generalize. And in real enterprise systems, the challenge does not end there. The model has to survive contact with changing data, changing users, and changing business conditions. This is why bias and variance matter. I hope this helped you understand bias and variance. Please subscribe to Scovia, and as always, stay curious.